Look at how a stick insect moves. Its 6 legs maneuver over twigs and leaves with effortless precision. That biological design is the blueprint for hexapod robots. We need that design because our most critical environments are rarely flat. If a machine is sent into the shattered concrete of a collapsed building for a search and rescue mission, it must be able to step over the wreckage. Traditional wheeled vehicles struggle here. A wheel requires a simple, continuous rotation forward to work, a mathematically straightforward mechanism. A hexapod leg introduces a highly specific mechanical chain, typically a hip, a knee, and an ankle joint. If you send raw electrical power to those motors without coordination, the robot will thrash and immediately collapse under its own weight. Walking is a computational challenge, requiring the synchronization of 18 different joints in real time. This diagram maps a continuous path in 3D coordinate space. Engineers calculate this route, known as a trajectory. As the robot advances, software monitors its center of gravity. This weight distribution must stay balanced so the machine doesn't tip mid-stride. Protecting that center of gravity leads to the next layer of instruction, the gait pattern. This is the specific sequence of leg movements the robot uses to walk. This schematic shows a quadrupedal gait. 4 legs remain anchored in a stance phase to support the body, while 2 legs lift for the swing phase. Locking this sequence into an alternating loop generates stable forward momentum. Planning a path and selecting a sequence are high-level instructions, but they are only effective if the physical hardware knows how much to bend to reach those targeted coordinates. There is a translation gap here. The software understands where the foot needs to go in abstract X, Y, and Z space, but the physical motors only understand rotational angles. To bridge that gap, engineers use inverse kinematics. It works backward from the target destination coordinate to find the exact joint positions needed to reach it. Looking at a leg in profile, we identify 3 specific angles to position the foot: the hip, knee, and ankle. Processing these through trigonometric equations ensures the foot's tip strikes the exact X, Y, and Z coordinate on the ground. The main controller must solve these complex geometric equations simultaneously for all 6 legs. The system repeats these inverse calculations hundreds of times every second to execute a single step. Inverse kinematics is the universal translator, converting abstract directional commands into physical motor execution. Running untested, complex kinematics on a physical machine can result in catastrophic hardware failure. A single calculation error can snap a joint under the robot's weight. To prevent this, engineers use 3D simulation software to test inverse kinematics and center of gravity calculations in a virtual environment. This allows programmers to identify balance failures and refine the robot's walk entirely in code before a single piece of metal is cut. When the code is finalized, the result is a fluid, organic stride. The movement of these machines is driven by thousands of mathematical equations, operating in continuous, invisible harmony.